Okay, so let us now explore the first law of thermodynamics in a practical problem, considering the case of an expansion engine. Okay, so in this case here we have air coming in with a certain set of properties, leaving with another set of properties. Note that another set of properties has less energy, right? So we expect our delta U, actually we know our delta U is decreasing from when it enters to when it leaves. And then at the same time we have heat being added to this engine and work being outputted as the useful work, right? The thing that this engine is doing. So pretty much gas is entering here. I think it's air, but it's entering here. It's expanding. As it expands, it's probably pushing things around. So that pushing a thing is the work of air being converted into mechanical motion, that is kinetic energy, which we then make use of. So let's read the problem statement. In a liquefaction plant, air flows through an expansion engine at a rate of 0.075 kilograms per second. The pressure and temperature of the air entering the expansion engine are 1.5 megapascals and minus 60 Celsius, and on leaving the pressure and the temperature are 170 kilopascals and negative 110 Celsius. The heat transfer to the air as it flows through the expansion engine is equal to 10% of the power output of the expansion engine. We are to determine the power output and the heat transfer from the expansion engine. So what's the case here? The idea is I'm going to apply the first law of thermodynamics, right? We know that the heat is 10% of the work, right? So we're putting 10% of the energy that's being outputted. Obviously, that does not violate the first law because we're also putting air that's leaving with a smaller quantity of energy, we can put it that way, right? So what is the idea? We're going to be applying the idea of energy conservation here. And because we're dealing with air, indeed it's air, so air is the thing that's going into this engine and then coming out, then we know that air can be approximated to an ideal gas, right? Because it's mostly nitrogen and oxygen. So in that case, things are a bit easier for us, right? This facilitates our life a bit. So what we need to do is we need to do a little control volume, and I'm going to use obviously this expansion engine here, which I just drew as a little horn-like thing, but it's just the idea that things coming in, coming out. So that's going to be my control volume, and we know that energy cannot be created or destroyed. That's the first law of thermodynamics, and that's what we're going to be applying to be able to solve this problem. Because check it out, if I redraw my engine, okay, so this is my engine simplified even more. Engine. What do we have going in? Well, we have air going in over here. We have air coming out over here. We have work being outputted, and we have heat going in. And that's what we're going to do. We're going to do a little energy balance using that as our control volume. And we know that within that control volume, the delta energy has to be zero. We can't create or destroy any energy, right? So if we were to write that down, what we're saying is all the energy that's going into the engine has to be equal to the energy that's going out of the engine. So we can say that we can talk about potential energy if we want. State 1, this is state 1 by the way, state 1, this is state 2, okay? So potential energy on state 1 plus the kinetic energy on state 1 plus the enthalpy on state 1. Remembering that enthalpy is combining both the internal energy and the flow energy, right? PV energy. What else? Plus the energy that's going to the Q, right? The Q that's going in, the Q going in. Minus what's going out. What's going out? Well, we'll have the potential energy of 2, the kinetic energy of 2, the enthalpy of 2, and then we also have obviously work that's being outputted. All of that has to be equal to 0. That's what the first law tells us, right? Now, on these sort of problems, note that nothing's said about velocity of any of the fluids, and there's no big change in height from this engine, right? That generally doesn't make sense to think about potential energy in these cases. So we go, okay, so if the potential energy on 1 is approximately equal to the potential energy 2, and because nothing was said about the kinetic energy, we can say they're also approximately equal. Then we're going to simplify things because we're going to say that this minus this is 0, and this minus this is 0. And this is rewritten in a very simple form, which is just the enthalpy 1 plus the heat going in minus enthalpy 2 minus work going out has to be equal to 0. If you think about it, what we're saying here is that the change in enthalpy, right, so this guy minus this guy, plus the heat that's going in is equal to the work that's being outputted, right? That's, again, first law of thermodynamics, another way to think of it, right? So the work being outputted is equal to the change in enthalpy, that is H1 minus H2, I think probably write like so because otherwise it might confuse us, plus the Qn. So all the energy that we're extracting is being used, all the energy we're extracting from the air plus the heat going in is being converted into useful work. Now, again, we can find all the things that we want to find here. One of the things we have to note when we're writing this equation is that the units, all these guys have to be the same. So I'm using small h there, which means that everything that I've written so far is given in kilojoules per kilogram. Okay, and we need to keep that in mind when we're solving these kind of questions, because or else you might run into trouble. We also know that the heat is 10% of the work, right? The heat is only 10% of the work. So we could rewrite this as H1 minus H2 plus work over 10, right? A tenth of the work. So again, this is just, okay, so that means that 9/10 of the work equals H1 minus H2, the change in enthalpy. Cool. So all we need is the change in enthalpy, so we can solve this and find how much work is outputted. Once we find that, we know 10% of that is going to be the heat. Because it's an ideal gas, remember that we can use the definition. You know, the DH is just, sorry, other way around. You know, CP is just how enthalpy is changing with temperature. And we can use that to our advantage in these cases, right? So we know that if I want delta enthalpy, big enthalpy, then I'll just do CP times delta T, and I'll have to add the mass there, right? And the mass is going to give me this guy in the unit of power. If I don't have the mass, then I'll just remove this, and this is still small h. Okay, so what are we saying here? Well, h, if I want to do h1 minus h2, take this out, h1 minus h2, then I'll just be CP for air, which is 1.004 kilojoules per kilogram Kelvin, and you can find this in any property table. Times the difference at temperature 1 minus temperature 2. And we know both these things, temperature 1 minus temperature 2. We know these things. We've been said in the beginning. Temperature 1 is minus 60. Temperature 2 is minus 110. And so minus 60 minus 110. Okay, and note that this is Celsius, but the difference is the same thing as Kelvin, so we can write it down in Kelvin. And we're going to get the answer in kilojoules per kilograms. Okay, so we get that this is about 50.25 kilojoules per kilograms, which is equal to H1 minus H2. Okay, so if you were to write H2 minus H1, if you do like the traditional delta enthalpy, then we have negative, which is saying that we have that surplus of energy that has to be going somewhere, because the gas itself, the air itself, is losing that energy, right? So we go back to our original question: what is the power output? But we also have been giving the mass flow rate. The mass flow rate is 0.075 kilograms per second. So if you want to then convert this unit here from kilojoules per kilograms into kilowatts, we can just multiply by the mass, and that will give us what I called before big H, right? So if I instead of wanting the small h's, I can just do this 50.25 and multiply that by 0.075, and that's going to give me I get about 377, so approximately 3.77, and then this becomes kilojoules per kilograms unit wise times the mass flow rate, that is kilograms per second. So these guys, right, and we're left with kilojoules per second, which is kilowatts, right? So this is kilowatts, and that is the big H. Now, know that from the equation that we drew before, big H, small h, okay. So from the equation that we drew before, this one here, okay, the unit of this guy is going to be whatever the unit of these guys are, right? So if I'll be perfectly fine for me to put this is my work output is given as 50.25 kilojoules per kilogram. But because I have the mass, because the mass flow rate has been given, then I can have this answer in kilowatts. And that's like something you always can do when you have the mass flow rate. And sometimes you want to find out the mass flow rate. If there's no way for you to find mass flow rate, then you're just going to leave it as kilojoules per kilogram. Okay, back to the 9/10. So 9/10 of the work output equals the 3.77 kilowatts. So therefore, my work equals 4.2 kilowatts, which is my answer, right? So this is useful work that's being outputted by the expansion engine. And the last thing that is asked of us is what is the Q, right? So what is the heat? And we know that Q is just 10% of work. So we just take that divided by 10. So we're going to get 0.42 kilowatts, which is yeah. All right. If you have any questions, let me know. And hopefully you find this useful. You can subscribe to the channel to be up to date with the latest videos and the explanations.